Hi friends, this video we are going to discuss about Gram-Schmidt orthogonalization process. Suppose V1, V2 and so on, Vn is a basis of an inner product space V. We can construct an orthogonal basis, that is W1, W2 and so on, Wn of V. Okay, using Gram-Schmidt orthogonal process. Why we require? Because V1, Vn up to Vn are the one basis of an inner product space V. We can construct the orthogonal basis. Why it is required? We know the well-known result. This result is more important result. It gives a nice simplification. Okay, that is a given idea. Let U1, U2 and so on, Un be a orthogonal basis of inner product space V, then for any V belongs to capital V, you can write as express in terms of inner product of V comma U1 divided by U1 comma U1 times U1 plus V comma U2 divided by U2 comma U2 times U2 and so on. Inner product of V comma Un divided by Un comma Un inner product, then multiplied by Un. These all are the coefficients. We can take Ci equal to V comma Ui, inner product of Ui comma Ui. This is called the Fourier coefficient. So any vector V belongs to vector space V, we can represent times in terms of basis, that is linear combination of basis, C1 times U1 plus C2 times U2 and so on, Cn times Un. We can represent, suppose U1, Un, U2 are basis. So we have to find C1, C2, Cn. So linear, that is some scalars. Suppose we know that u1, u2 are the standard basis. So this orthogonal basis means we can directly find using this Fourier coefficient formula. So whenever given base is there, we can convert to the orthogonal basis. We can easily find their C1, C2. So that is why we required orthogonal basis to implement very easiest way. So that is the reason we are going to convert given basis to orthogonal basis. This is called orthogonalization process. This process we have done by classical Gram-Schmidt orthogonalization process. First, we are going to explain the process. Suppose V1, V2 and so on Vn is a basis of an inner product space V, we can construct orthogonal basis W. First we start with W1 as equal to V1. Then W2 equal to V2 minus inner product of V2 comma W1 divided by inner product of W1 comma W1 times W1. Then W3 equal to V3 minus inner product of V3 comma W1 divided by inner product of W1 comma W1 times W1 minus inner product of V3 comma W2 divided by inner product of W2 comma W2 times W2. This is the process we proceed. So finally we are taking as Wn equal to Vn minus Vn comma inner product of W1 divided by W1 comma W1 times W1 minus V inner product of Vn comma W2 divided by W2 comma W2 times W2 minus and so on. Finally Vn comma W n minus 1 divided by inner product of Wn minus 1 Wn minus 1 times Wn minus 1. This way define these all the vectors are orthogonal basis. Let's begin with an example 1. Let U be a vector space, we take inner product space, be an inner product space that is inner product of V inner product of U comma V equal to U transpose times V vector. This is simply a dot product, inner product space. It is spanned by V1, V2, V3, where V1 equal to 1, 1, 1, 1, V2 equal to 1, 2, 4, 5. V3 equal to 1 minus 3, 4. So 1 minus 3 minus 4 minus 2. So now I want to convert the orthogonal for the U. Okay, how I can start with? I start with W1 equal to V1. As it is, I take it. Then what is the V1? V1 is 1, 1, 1, 1. This is my W1. What is the W2? W2 is V2 minus inner product of V2 comma W1 divided by inner product of W1 comma W1 times W1. What is the V2? V2 is 1, 2, 4, 5. Inner product of V2. Inner product of V2 is, that is V2, that is 1, 2, 4, 5. That is V2 transpose times W1. W1 is all are 1. Divided by W1, W, inner product W1 is times, we can write it as 1, 1, 1, 1. So what will come is, this is 1, 2, 4, 5 minus this one is 1 plus 2 plus 4 plus 5 divided by 4, then it will come 1, 1, 1, 1. This is 12 divided by 4, that is 3. Then 1, 2, 4, 5 minus 3, 3, 3, 3. So you will get the vector as minus 2, minus 1, plus 1, and plus 2. This is my W2. Now we go for the W3. What is the W3 formula? W3 is V3 minus V3 comma W1, inner part of W1, W2, W1 times W1, this is W1 minus V3 comma W2 inner product divided by inner part of W2 comma W2 times W2. Now you apply what is the V3, that is a column vector 1 minus 3 minus 4 minus 2 minus V3 comma W1. What is the V3 is, we already defined, that is the V3 transpose is 1 minus 3 minus 4 minus 2 times W1 is 1, 1, 1, 1. The norm of, that is W1 divided by W inner product is, we already found that is value is 4 times, this is a some scalar value, times the vector 1, 1, 1, 1 minus V3 is 1 minus 3. The same way we can write down. That is 1 minus 3 minus 4 minus 2. W2 is now only we calculate minus 2 minus 1 1 2. So minus 2 minus 1 1 2 divided by minus 2 minus 1 1 2 times minus 2 minus 1 1 2 times, this is the scalar value only because this is the 1 by 4 matrix, this is 4 by 1 matrix. If multiply you will get the scalar. Similarly the denominator also. Then so the first vector is 1 minus 3 minus 4 minus 2 minus 1 times 1 minus 3 minus plus minus 3. So it simply add everything. You will get it as minus 9 plus 1. You will get it as minus 8 denominated by 4 times 1 1 1 1 minus the same way if you are multiply you get 1 times minus 2 plus 3 plus minus 4 minus 2. So if you get, you will get the answer is minus 7 divided by this value means plus 2 plus 1 plus 1 plus 4. So you get the 8 plus 2 is you get the 10 times. So that vector I must retry. That is minus 2 minus 1 1 2. So you apply minus 2 minus 1 1 2. If you are able to, this is the plus, it's a 2, it is 7 by 10. You get that the first value is 8 over 5. The second component value is minus 17 over 10. Minus 13 divided by 10. Then final value is 7 by 5. This is the W3. The same three vectors, it's become orthogonal is W3 is 8 over 5 minus 17 over 10 minus 13 over 10 and 7 over 5. Please verify it. Okay. So it's a given set of non-orthogonal vectors, we can convert to the orthogonal vector. It need not be the Euclidean space, non-Euclidean space also you can find. That is my another example. Let V be the vector space of polynomials f of t with inner product f comma g equal to minus 1 to plus 1 f of t times g of t dt. So apply Gram-Schmidt orthogonal process. It's a process to 1 x square 1 t square t cube. So how I can to find it? Okay, so I start with that. This is my basis, I can say. Now first of all, v1 equal to, this is my u1, sorry, this is my v1, this is my v2, this is my v3, this is my v4. So I want to convert as a w1 equal to v1. So my w1 equal to 1. What is my w2? w2 equal to v2 minus inner product of v2 comma w1 divided by inner product of w1 comma w1 times w1. What is the v2? v2 is t minus inner product of t comma 1 divided by 1 comma 1 times 1. So what is the inner product of w1 is inner product t comma 1 equal to integral over minus 1 to plus 1 t times 1 t, so it's become dt. This value is 0. Why? Because it's an odd function, the minus both are 0. So this is 0, so everything becomes 0. So w2 become t only. What about w3? v3 minus v3 comma w1 divided by w1 comma w1 times w1 minus v3 comma w2 divided by w2 times w2. So what is my v3? v3 is t square minus inner product of t square inner product of 1 divided by 1 comma 1 times 1 minus inner product of t square, w2 is t divided by t comma t times t. So what about the inner product of, now I want to check, I want to find these guys, that is Fourier coefficient t square comma 1 equal to g minus 1 to plus 1 t square times dt. If you are integrate, you will get t power 3 divided by 3 minus 1 to plus 1, you will get it as 2 divided by 3. 2 divided by 3, that is t square comma. Then what about this one? Inner product of t square comma t equal to inner product of minus 1 to plus 1 t power 3 dt equal to 0, because this is the odd function. So inner product of 1 comma 1 is minus 1 to plus 1 times 1 times d2, you will get it as 1, 2 only you will get, correct? the 2. So then your W3 become T square minus 2 by 3 divided by 2 times 1. So it's nothing but T square minus 1 over 3 you will get. That is your W3. Now we want to compute what is the W4. W4 is V4 minus inner product of V4 comma W1 divided by inner product of W1 comma W1 times W1 minus V4 comma W2 divided by W2 comma W2 times W2 minus V4 comma W3 divided by inner product of W3 comma W3 times W3. What is the V4? V4 is T cube minus V4 is T cube comma W1 is 1 divided by inner product of 1 comma 1 times 1 minus this one is V4 is T cube. What is W2? W2 is T itself. So inner product of T divided by T comma T times T minus V4 is T cube. W3 is T square minus 1 by 3 divided by T square minus 1 by 3 comma T square minus 1 by 3 times T square minus 1 by 3. So clearly this guy is going to 0 because from assumption this is the inner part of odd function only will come. This guy also become T square, this will come also, this is also 0, only this only we have to evaluate. That is T power 3 comma T equal to integral over minus 1 to plus 1 T power 4 times dt. You will get 2 over 5. Inner part of T comma T is minus 1 to plus 1 T square dt. You will get the 2 over 3. So then your W4 equal to T cube minus 2 over 5 divided by 2 over 3 times T. So then these guys, if you simplify these two will cancel. So T cube minus 3 over 5 because these two will cancel. This is your W4. So thus orthogonal bases are 1 T square minus 1 over 3 and T power 3 minus 3 over 5 times T. These are the orthogonal bases of the given vector space. I hope this video you understand how to calculate the orthogonal basis using Gram-Schmidt orthogonal process. Thank you for watching this video.